Hi, everyone. My name is Kelly. I'm a graduate student at Marco Bernardi's group at Caltech, and welcome to the Lecture 5 of Perturbo Workshop 2025 for Ultrafast Electron Dynamics and Spectroscopy. In this lecture, I will cover Perturbo's main feature of computing carrier population dynamics using the Boltzmann transport equation formalism. I will talk about the practical applications, theory, computational workflow, and 3 different examples showcasing the latest capabilities of the code. Am I heard by everyone? I just wanted to make sure. I'm not muted, right? Okay, good. So after this lecture, we'll transition into a brief time of questions. Then starting from around like 9:30, we will start our hands-on session where we will practice using Perturbo to simulate electron dynamics in a palm probe experiment. So feel free to post any questions in the chat and we will answer them after this talk. So for the problem of ultrafast carrier dynamics, there are many theoretical methods that can be used to simulate these problems. But different methods are suitable for different scenarios and addressing different physical questions. So for example, the time-dependent density functional theory is a very common method to describe the evolution of electronic wave functions by solving this time-dependent Kohn-Sham equation. It captures the coherent electron dynamics and as well as the effect of electron-electron interactions really well. But since the key quantity here is the wave function, the time steps are usually on a time scale of attoseconds. And it makes it a very expensive calculation to simulate to longer time than hundreds of femtoseconds. There are also other methods for studying carrier dynamics, such as the non-adiabatic molecular dynamics or NAMD in that case. You can also have non-equilibrium Green's functions. And these methods are not covered in today's lecture, but they're also suitable for different types of problems. The focus of the talk today will be the main theory used by Perturbo, which is the Boltzmann transport equation that is based on many-body perturbation theory. The key quantity here is not the electronic wave function. We do compute many first principle inputs from DFT, but this is not directly simulated. The electronic wave function is not directly time evolved in Boltzmann transport equation. The key quantity instead is the F and K, or the electronic populations as a function of time. And because we're simulating populations, this is a semi-classical method. It captures all the incoherent effects of electrons as well as other quasi-particles. And it's basically an equation that sums up the collision integrals of the electrons or charge carriers with other quasi-particles as well as the external field. And for these types of calculations, because the electron-phonon interactions are often the key focus of simulation, or even other interactions such as phonon-phonons, the time step will be on the order of femtosecond. So this is more suitable for a longer simulation from femtosecond to pico, even to nanosecond range. And so if you want to capture the effects on this time scale, Boltzmann transport equation offers a framework to compute these carrier dynamics with relatively small computing cost. So the theory of BT was already covered in yesterday's lecture. So if you want to revisit those, I encourage you to do so after today. The current RTBT implementation in Perturbo addresses many problems of non-equilibrium dynamics, such as the things I listed on the top row. For example, there is the carrier cooling mediated by phonons, or you can compute the velocity field curves, which are the drift velocities as a function of electric field. And you can also compute the differential absorption signal as one of the latest features that we will be showcasing today. And for the future releases, we hope to incorporate more effects, for example, exciton-phonon interactions, for non-equilibrium dynamics, of course, and then perhaps spin relaxation. And what's currently under development is the lattice dynamics, which captures the effects of phonon-phonon interactions. So just to recap the basic formula of the Boltzmann transfer equation that we talked about yesterday, which was more focused on the transport side. Today, we will want to use the same equation for dynamics. This is, again, a semi-classical method based on many-body perturbation theory. And in Perturbo, we assume that it is a homogeneous material. The electronic excitations for RTBT should be provided by the user as a starting initial condition. So you need to know what the initial condition will be. And then the electron dynamics in the current release of the Perturbo is the sum of the effect of the electron-phonon collision integral IEPH as a function of the electron populations and the external electric field E, which contributes to this advection term on the right-hand side. So here I just like to briefly go through the namings. N is the band index for electrons or holes. K is the momentum. And the time derivative of the electronic populations is the sum of the collision integral IEPH of electrons and phonons. And then there is an implicit population of phonons also in this collision integral, which we name it as big N nu q, where nu is the phonon mode index and q is the wave factor. So for the current release, the NUQ is fixed, is independent of time, and is given by your initial phonon bath temperature and a Bose-Einstein distribution of that. But in the future release, we hope to incorporate time-dependent phonon populations as well. So you can see the phonon drag effects. So for this collision integral, which we also covered yesterday for a little bit, I just want to give a recap. It is the sum of over the entire reciprocal space of this G matrix, which is the electron-phonon scattering matrix elements in the momentum space that are computed first from DFPT and then linearized interpolated using Perturbo. And it is timing the product of these two sums, which is the emission term and the absorption term. So this emission term has an energy delta function in front of this, as well as the absorption term. It basically ensures the energy conservation of these scattering processes that are listed below. And we see that here the emission term incorporates both the electron population at different band index and momentum, as well as the phonon population. But here, only the electron populations are updated and time dependent. So this F emission and F absorption are both time dependent. And in Perturbo, I would like to stress that this energy delta function, of course, numerically wouldn't be an exact delta function. And we currently use a Gaussian with a smearing to approximate this energy delta function. And the user should also converge over the smearing or the delta, the width of this Gaussian function, and for these dynamics results. This is the same as the transport calculations. If you would like to learn more about the theory, I also encourage you to read the seminal paper here where we publish about Perturbo. So after the theory introduction, we can move on to the workflow of ultrafast dynamic simulation. So the first step is setting up the dynamics. You'll see that this setup calculation is very similar to the setup for all the transport calculations that we did yesterday. And here in setup calculation, we are already assuming that you have an EPR file that we have generated through using QE2per.x, which we showed yesterday. And starting from the EPR file, now all the dynamic simulations only use Perturbo.x or the Perturbo-Pi post-processing tools. So the first step of setting up is using the calc mode that's called setup to set up the energy band and the energy and band windows as well as the momentum grids, so that we can have a minimal number of grid points or electrons that are involved in the calculation. And then after setting up, we move on to dynamics, where technically the dynamics run is all done in one step, but you can also break into different steps. The calc mode is always called dynamics run. In this case, you first set up and compute and then store these electron photon scattering matrix elements, and then you choose in your input file the initial carrier populations. You can either do a one snapshot initial condition at t equals to 0. So I'm looking at f and k t equals 0 here. You can set it up as Fermi-Dirac distribution at a certain temperature, or a Gaussian Lorentzian pulse, or you can set it up as restart, which will pick up the output from the previous dynamics run and simulate from the last time snapshot. So you can break your simulations into multiple ranges so that you don't have to submit a very expensive calculations. And then besides the one snapshot initial condition, you can also use, which is a new feature, a series of additional electron population as simulating a pump pulse effect. And this we'll talk about in the hands-on section with more details. So with the initial condition setup, now we're ready to time evolve the Boltzmann transfer equation to compute the time-dependent electron hole populations, F and KT. So with this F and KT, which is stored in an HDF5 file, we can then use the calc mode dynamics PP to compute the electron population as a function of energy and time, which is often a useful visualization to see. And this is done using tetrahedron integration to ensure accuracy. So this is also a result that will be stored in HDF5 file, and either F and KT and F as a function of E and T can be visualized using tools in Perturbo-Pi, or you can write your own script to read this HDF5 file and plot things that you want. And Perturbo-Pi also offers a new function to compute the differential absorption signal delta A as a function of the energy and time, which we'll show later as well. So now I will transition into showing the 3 examples of perturbable ultrafast dynamic simulation that I just mentioned. The first one and the first 2 will be covered, was covered already in the last workshop 2023. So if you want to have a detailed simulation, like an example, you can go to that page and look at all these examples that we provided. But the last example here will be practiced later in today's tutorial. So for the first example, we have a very basic carrier relaxation problem. It simulates the relaxation of excited electrons. And the Boltzmann transfer equation without an external field will just reduce to one with electron photon scattering only. The simulation parameters here are provided just as I said earlier. You can start the electron populations in a Gaussian excitations, for example, in terms of energy, so Gaussian in the energy profile. And we are currently plotting the electron populations as a function of energy on the right-hand side, and you can see that it's a Gaussian. We need to set the phonon temperature to a certain number, and here we're using the room temperature, and I'm using the time step of about 1 femtosecond, which is a good parameters to start with, but you also need to make sure that this is a converged time step. And in this example, we use the Euler solver for time integration. So if you run the simulation in Perturbo, you'll see that the electron populations will slowly cool to eventually a Fermi-Dirac distribution at 300 Kelvin. The second example is more interesting, where we have the effect of an external field. So the Boltzmann transfer equation now has the advection term with the field. And something that people compute a lot is the drift velocity of electrons at thermal equilibrium, at steady states, as a function of this electric field. So in some materials like silicon on the left-hand side, the drift velocity is linear at low fields and it saturates at high fields. But for certain materials such as gallium arsenide, the drift velocity displays a gun effect where it can decrease after a certain electric field. And these fields are all pretty high in numbers. And with the Boltzmann transport equation, compared to other simulations like Monte Carlo, it provides a framework that is parameter-free for these electron dynamic simulations at high electric fields. But there is a computational challenge, which is that for these high field dynamics, with electron-phonon interactions, you want to time step use very small time steps, like 1/5 to capture the electron-phonon interactions, but to simulate to very long times in order to reach a steady state to compute the drift velocity. So if you're interested in computing electron population at a certain field, depending on what feature that you're looking for, such as the drift velocity, instead of computing a data point for every single electric field, so computing one dynamics and reach to steady state for every single dynamics, there's one smart way that you can use Perturbo to simplify this calculation. So here we're using the drift velocity field curve as an example. So you want your time-dependent carrier population so that you can compute this transient carrier velocity, which at time equals infinity, it becomes the drift velocity of the system. So you're in a steady state. So the procedure will go as follow. You will start with an initial condition where the electrons are at a thermal equilibrium, like the Fermi-Dirac distribution. And then you apply the field. But the goal is to simulate to, for example, a very high field and cover all the data points from 0 to, for example, 2000 volts per centimeter. You first apply a very small electric field, for example, 100 volts per centimeter, and then you time step RTBT until the steady state is reached. So you see on the left-hand side, we expect the carrier population to drift to a higher energy, and then the drift velocity is also non-zero after you reach the steady state. The next step will be increasing this field to another level, for example, 200, and then do the time evolution of RTBT again until a new steady state is reached. So after this new steady state, it's easier to compute because you start from the previous ending electron distribution. So you save the time evolving from E equals to 0 again. And then you now can arrive at a new drift velocity for the new electric field. And then you just keep going until you cover all the electric field points. So if you look at the entire simulation as a function of the simulation time, it will go like this, where the electric field is ramped up and your transient velocity has these staircase feature, and then you can compute the drift velocity once you reach steady state for every single time step. So if you're interested in learning more about this, you can look at this paper published by our previous postdoc, Ivan, where we use this method to showcase drift velocity in silicon, where we were able to reproduce with very good agreement with the experiment, the electric field anisotropy in different values of silicon. And another example that we showcased in this paper is the drift velocity in gallium arsenide, and we were able to find this negative differential mobility that signifies the gun effect in the system. And we are also able to, with this theoretical simulation, see where the electrons are contributing to this effect. And we find that it was mostly the L valley populations. So the last example will be a new feature in Perturbo. It is essentially the first example, but with additional electron distribution as the user that can be customized by the user. So instead of just a collision integral, you have this big F pump as a function of time. That will be specified by the user. And Perturbo-Pi, the post-processing tool, also provides a functionality to generate these pump pulse right-hand side functions. So this will be a perfect tool to simulate, for example, transient absorption in pump probe experiments, where for these experiments, you excite a system with a pump pulse at time equals to 0, and your pulse will generate pairs of electrons and holes in the system, and then you will send a probe pulse after a certain amount of time to probe the relaxed carriers and see the effect of this excitation. So with RTPTE, we are able to compute the subsequent dynamics of carriers and then use this population to compute the transient absorption signal, which I plot on the right. This is an experimental plot, but we can simulate something like this where we can get something that the experiment usually measures. So the workflow will look like this for transient absorption. Essentially, instead of a given Fermi-Dirac or Gaussian pulse, you'll set up your own pulse HDF5 file with Perturbo-Pi or a custom input that's of the same format. And this pump in Perturbo-Pi will be proportional to the P, which is the transient dipole amplitude that you can compute from other softwares. And then it's a Gaussian in time, as well as a Gaussian in energy. So you first compute your transient dipole amplitudes, or you just leave them as a constant, and then you read them in to generate these snapshots of F pump. And with these snapshots, we're now ready to time evolve the RTPT. So the following equations will be time evolved, and then with the populations, you can get the transient absorption signal with Perturbo-Pi or compute other quantities that are interested. And then I just wanted to highlight this transient absorptions signal that we can compute. The formula is on top, where it's a function of the transient dipole amplitudes that you can potentially use YAML to compute, and then the electron and hole populations that you generate, as well as an energy delta function. So for example, this is a simulation done that signifies gallium nitride. And you can see that as the simulation time goes on, the transient absorption signal shows a carrier cooling from this point to this energy. And we'll be doing something very similar today with a much smaller grid. Finally, I just want to highlight some of the features in Perturbo Ultrafast Dynamics. In the previous releases, we already implemented the restart function where you can pick up the last simulation and keep going. You can also load the pre-computed electron phonon matrix elements, just like the transport calculation, where once you set it to true, using the same number of MPI tasks, you don't have to do the scattering matrix interpolation again. You can also exclude phonon modes, just like the transport calculations. You can select the phonon modes that you're interested in to see the different contributions to the dynamics. And finally, you can also stop the dynamics for certain, for the electric field case, where once your drift velocity is converged, then the dynamics will stop automatically. So you don't have to look for a steady state. In the new Perturbo release, we have a GPU support for ultrafast dynamics that was covered yesterday, where we have a better data structure for both CPU and GPU. If you if you compile Perturbo with GPU and specify this scat IMPL equals the target TGT instead of the standard STD, then you can use the GPU feature to expedite your simulation. And then finally, we want to highlight that we can compute the transient absorption signal and simulate a palm pulse generated. So the electron and hole population generated with the palm pulse using the latest version of Perturbo-pi and Perturbo as well. So to summarize, we introduced Perturbo's capabilities to simulate the real-time electron and hole population dynamics that is dominated by the electron phonon scattering and external fields. So it is able to reach longer time scales from femtosecond resolution up to hundreds of picosecond, even to nanosecond, depending on the system. And it's efficiently parallelized, just as the transport. It supports both GPU and CPU calculations. And finally, it's very, very flexible as well. So it can either do electrons or holes separately. It can also simulate different types of initial excitations with different built-in methods or user input. It can also simulate high field dynamics. And finally, I just want to highlight the features that can compute ultra-fast transient absorption signals. In the future, we hope to incorporate other excitations as well as different time integration methods. So one work that's already published, which is mine, uses adaptive and multi-rate time integration with the sundials library that will make the simulation much faster. So we can simulate the phonon dynamics, which are more time computationally expensive. And then we also hope to publish these features with different interactions in the future in our Perturbo-code. Okay, so this, I think, is the end of my talk, and I would love to answer questions if there are any. Any questions from the in-person participants?
So you said that you need to provide the initial electron operation for the calculations. How do we choose that as like a material dependent quantity for, let's say, semiconductor or insulator metal?
Yeah, so you're saying the question is, we need to provide the initial condition for the excitations, and how does it work? So Perturbo has a couple built-in methods, such as the different types of initial distributions. If you know your pulse pulse strength and all these spectral width, then you can use Perturbo-pi to generate these. And the only thing that you need to know is the carrier concentration, or essentially after your pump pulse or after your excitation, what's the carrier concentration in your system. And this you can use these tools to match the carrier concentration. And also it works for other initial distributions like Fermi-Dirac distribution. You can also compute the carrier concentration using Perturbo. It's called Dynamics PP, the post-processing features to match the carrier concentration, and then you'll be able to know. Yeah. Any other questions? Right.
Okay. Also, if there's any questions on Zoom, feel free to put those in the chat. And then if not, we'll get started on the hands-on part of this.
Okay, so I guess before we start the hands-on session, I will pause sharing, and I would encourage you guys to download the Perturbo Hands-on 5 GitHub repo. Yes, let me take a look. So if you haven't downloaded these EPR files, we should start here. I think I have these required files with these links. So if your computer is not the fastest, or you're not using parallelization on your computer, this tutorial is very calculation expensive, so I would suggest downloading the example with reference results so you can use some of the temporary results to make the simulation faster, and you can download it here in this box folder. If you're very confident about your computer, then you can download the tutorial itself here on GitHub. And you should check that this folder contains 3 Python scripts. As you can see on the right-hand side, it contains these 3 scripts, as well as the band folder. And then you can also download this gallium arsenide EPR file in this tutorial here. And you can move this EPR file into this hands-on 5 directory, which we will start from right here. So in this hands-on session, we'll practice Perturbo by simulating this carrier dynamics in a pump probe spectroscopy in gallium arsenide and compute the transient absorption signal from the resulting populations. So you can post any questions, and I will have pauses during this tutorial so that you can ask questions in the middle so that we can all follow and go through it together. For this typical palm pro experiment, I just wanted to give a brief description of example problem. Usually, after a few tenths of a femtosecond, you can describe these electrons as already thermalized internally due to electron-electron interactions into a hot Fermi distribution with a higher temperature. But in this example, we'll be explicitly modeling this additional electron hole occupations generated by the pump holes and the subsequent dynamics that contribute to the absorption signal. So the problem will be, for the theory problem, is that from t equals 0, we will simulate the pump pulse by adding additional occupations into the system until the duration of the pump. And then after that, we won't add any extra populations. We'll just time evolve the dynamics with EPH interactions. And the phonon bath will be set to 300 Kelvin in this case, but you can set it to be a different number for your own simulation. So I guess in this tutorial, we'll go through preparing the input files for calc mode equals setup, dynamics run, and dynamics PP. We'll also do a simple analysis of the results using Perturbo-pi. Okay, so hopefully everyone has downloaded the files. I know this EPR file can be a little bit big. If you haven't been ready, we can still start setting up the environment, which we will use Docker to demonstrate. Here, I'm using GCC OpenMP just because I use a MacBook. You can also use iFort, and instead of using OpenMPI threads, if you're using MPI parallelized environment, just use MPI run with the number of tasks and impulse. So I will just use GCC OpenMP, and because I'm using this, I'll set my OpenMP threads to the number that matches my computer. So after running this, we'll see we have this hands-on 5 folder, and this is exactly the folder that's in my computer. And I will set my number of OpenMP threads to be 10. If you don't set it, then it will just be automatically running as the number of cores in your computer, which is also fine. So if you used a different number of MPI tasks in this tutorial, you'll find that the temp folder I provided as the reference is not useful if you use more than one MPI task, but you can just do your own calculation and the physical results should agree. It's just that there are some temporary files that depend on the number of MPI tasks that you use. So first, we'll start with the setup calculation. Just But before setting it up, we want to look at the bands to see if how many bands we want to include and what's the energy range in these bands. So I have prepared the bands folder with all the necessary inputs. If you can see that there's 3 different files. The last one will help you plot the bands, and then the first one, if you take a look, it will show the high symmetry path that you can visualize the bands. And then we can also look at pert.in, which is the input file that has calculate mode equals the bands. So now we first interlinked the EPR file as we talked about yesterday in yesterday's hands-on session. So I store my EPR file in the directory above. So that's where I link it. And I suggest you to move there as well. So now we have the linked EPR file and we're ready to run the bands calculation. So if you're using multiple MPI tasks, which is not really necessary for this run, you just simply do this command here with the number of tasks that you want. But I only have one MPI task, so I'm just going to run it and visualize the output. So then we can use Perturbo-pi to visualize the bands that we just plotted. The script is here called plotbands.py. I want to see where the band conduction band minimum and valence band maximums are. I already know that there are 4 valence bands. That's why I'm like looking at like this, but you can also see more information on Perturbo-pi to see how to find these points. So if I just run plot bands, it will tell me which energy values are my conduction and valence bands and tell me the direct band gap because gallium arsenide does have a direct band gap. And we know that we want to simulate a certain pump pulse. For example, in this example, we're doing 1.5 electron volts. And with a band gap of 0.9, you want to have enough energy range to incorporate all the possible transitions. So in this example, I'll do about 0.7 electron volts in the electron bands. And because the whole bands don't really matter that much for gallium arsenide, so I'm just going to use a smaller window for holes. But in reality, you need to make sure that your energy range is converged, your results converge with the energy range you select. But in this case, I'll just select these Emin, Emax, these energy ranges. So it covers about 0.3 electron volt below the valence band maximum and 0.7 above the electrons. I chose these range so that the simulation can run faster, but you should include more just to make sure that your results are converged. So if you look at what is generated, there's this PNG file that you can open. It will show you the plotted energy range that I just chose. And we indeed see that there are 4 valence bands. So we can just include band number 2 to 4 for holes and band number 5 for electrons. So if you look at this point here, it's just below band number 6. Okay. So after knowing the band structure and selecting an energy range, we can finally do setup. Any questions to this step? Okay. So for setup, we have to do it separately for electrons and holes, but we need to do both if you want to use Perturbo-pi to generate your pump pulse, because you're generating pairs of electrons and holes. But if you have your custom input, you can simulate electrons or holes only. So in this case, we'll first make a folder for electrons, and then instead of doing the per setup, per trans as different folders, we'll just have everything in the same folders for the sake of time, because we're reusing a lot of the files that are generated. In this folder, we also need to link our EPR file again, and then we will first create the temper file, which is easy to forget, so I'm going to do it first. In this case, we don't have an external magnetic field for transport, so we will just have line 1, which says that we have one line and the phonon bath temperature 300. And the carrier concentration, we want to compute it, so we're going to leave it 0 here. And then some, sorry, this is a chemical potential. Let me move this. The chemical potential on the second one, and then carrier concentration on the third one. Unfortunately, so the setup calculation will compute these values, but in ultrafast dynamics, what's really read in the dynamics run is just this one and then the phonon bath temperature that you specify. So these don't really matter because the carrier concentration is actually set by your initial condition in the dynamics input, not gas temper. So we can just put it here, and then we can create a new input file setup in. You can use interactive workflow on Perturbo website under utilities, or you can use since we're already in the Docker, we can use input generation. So let's go back to hands-on 5 and see that at ELEC. We can use input generation with calc mode equals setup, and I want to name my file setup in, so this is what I'm typing. And now we can modify the setup in. So this is the standard generation, but we want to put our prefix here, and we want to specify a grid. So if you're using your personal laptop that doesn't have like 12 cores, or at least I would say 6 cores or 4 cores, I would strongly suggest you download the temp folder if you want to follow the exact numbers here on the simulation. If you download the temp folder, you have to follow the exact inputs to use those. But if you want to run on your own computer, I suggest putting a k-dimension of 24. The results won't be physical anyways, not even for this example, but it will make the calculation run. So I would put 24 all here if your computer is slow, but for mine, I'll just put 60. And then you put your temperature file name here. And then I want to specify my energy and band window to make the calculation faster. So I will only include for conduction band number 5. That's why the min and max is number 5. And then I found a good range that includes the entire band number 5 that I am interested in. So I'll put these number here. And if you want to find your E Fermi, then you can find the Fermi energy. But if you don't want it, then you can leave it to the false. But I just want to find it just in case. And then here, Hall equals to false because we're doing carriers. Okay. There is this Bose QDIM, which is not really used in the setup calculation, but will be used later in dynamics run. You can put it here, but it's not going to be read. In the future releases of Perturbo, it might become important.
Oh, I think there's a question in the chat.
Yes.
You want me? I can read it.
Yes.
Yeah. So, question is: hello everyone. When I use ln-sf with the EPR file, the run doesn't work. Missing the gallium arsenide EPR file. Did I miss something? File is a dangling symbol.
Sounds good. Thanks. Thanks for the question. So the question is about the gallium arsenide EPR file. It can be found here through this link under the required files. And if you click on this link, you'll find this EPR file right here, and you can just download it and put it in your hands-on 5 folder. So if I go back to hands-on 5 folder, we see that the gallium arsenide EPR file is here. So whenever you create a new folder, you can do the link to the parent directory, like what I did.
And it should work if you link it. You don't have to necessarily copy it, right?
Yeah. Okay. So we were doing the setup calculations for electrons, and now we are ready to run the setup calculations for electrons with gas temper, EPR, and setup. So now we have generated some new files. We have this density of state, doping, temper. So if you look at the gas temper, we found our new Fermi, which is at this level for this carrier concentration. The carrier concentration changed from what I gave because our grids are really sparse and it has to sum over the grids. If your grids are dense enough, then this concentration would not change much. And the file that we need to keep is the tet.h5 file, which will be used that stores our grid point information. We will do the same for holes. So for holes, I will copy paste some of these make comments and input files. So you make another folder for holes, link your EPR file, and then create a gas temper. Sorry. You can just copy paste from the workshop. And then I'll also copy paste the setup in where you see that everything is the same. You have to use the same K grids if you want to generate your pump pulse using Perturbo-Pi. If you just want your whole calculation or electron population, then you don't need to specify it to be the same. And then the only thing different is the whole equals to true in this case, and we have a different range of bands and energies. So I will copy and paste to setup.in and then run the setup calculation. Okay. Any questions up to this point? Okay, so now is the most expensive calculation of all times. We can set up our carrier initial populations. So what you can do is you can provide your own HDF5 file, which we'll show later. Or you can use Perturbo-Pi. But for Perturbo-Pi to work, it wants to read certain files. And we want to provide a cDyna file as well as a YAML file that signifies what's going on in your grid size and dynamics. So what we typically do is we run dynamics for one single time step. That's like a fake dynamics, but it will compute the electron phonon matrix elements and store them, and also create a sample cDyna file and a sample YAML file. And then we will use Perturbo-Pi to generate these. And you need these for both electrons and holes with the same electronic grid. The same electronic grid, but not necessarily the phonon grid. And in cDyna elec, we'll start with a new input file pulse in with the calc mode dynamics run. So I will do input generation, dynamics run. Hopefully that's the right thing. And then call pause in. So there are different things that we want to modify. I will, for the sake of time, I won't actually modify it. I'll just copy paste this and start running the code. And while the code is running, I'll explain these parameters. So I'll just copy paste. And then to run, I strongly suggest you parallelize this calculation. You can use this to run, or if you want to run it in the background, you can use the ampersand to run it in the background. So I'll just run it in the foreground here. So now I start computing electron phonon matrix elements. And this is pretty much the only calculations doing in the entire Dynamics Run workflow that is the most time expensive. So if you are seeing that this is not generating anything, then maybe you should use a smaller grid size. So now we can explain our parameters here. So we need to use the same K-grid as before, as we did in setup for the electrons, and the same gas temper file, which because we're in the same folder, so we don't have to copy paste it. And then for Dynamics Run, calc mode, there are certain groups of parameters. The first one is the times integration. So time integration has these three plus the solver that specifies it. Both in step is the number of time steps you want. And output in step is how many time step you want to give an output. So you don't have to store every single time step in your output file, which will be a gigantic file. And then the time step is the delta t in your calculation, where the Perturbo will time evolve for every single time step, which is in femtosecond. So for example, you have 1,000 steps for both in step, and then time step is 1. You want to output every 20 step, then you will end up with an output file of 50 steps, and they're spaced out in 20 femtoseconds. And then the solver parameter will give you an option for either Euler or RK4. In the future, we want to have more advanced solver published for Perturbo. That will make things very fast. And the next set of parameters is initial contribution, the initial electron distribution, which is the Bose-init dist, and Bose-init E0, smear, and amplitude. So the Bose-init dist, if you set it to restart, it picks up the previous cdyna file in the folder, and then prefix.cdyna file in the folder, and then run with the last population snapshot. If you type restart, then these three lines, Bose-init 0, smear, amplitude, are not going to be used. But if you use a Gaussian or Lorentzian, these three will be the E0 will be the center of the Gaussian or Lorentzian, smear will be the width, and then or the sigma in each case, and the amplitude will be the prefactor for Gaussian and Lorentzian. This amplitude is default 0.1. So if you don't want any of them, then you have to specify it to 0. And finally, we also have Fermi-Dirac. In that case, you will say Fermi here, and then you will have the smear to be the temperature of your system of phonon bath. Temperature of your electrons. So you want to start with, for example, 2000 Kelvin, then you convert it to milli-electron volts and put it here. The Bose-init E0 is your chemical potential in this case. And the amplitude will not be used for Fermi as init distribution. If you want to use a pump pulse, then it doesn't matter what you put here, it's not going to be used. You just specify the amplitude to be 0 and set the last line pump pulse equals to true. And then it will read the file name that you name here in the same folder and read the pump pulse HDF5 file. Because we're generating the EPH matrix elements first as a mock dynamics, we won't be reading any pump pulse. We will be generating the pump pulse after this run. So after that, we'll set this to true. There is the last group of parameters, which is delta smear and frequency cutoff. If you delta smear is the smearing of energy conservation. So we approximate the energy delta function in the scattering processes as a Gaussian. So you want it to be about 10 MeV, depending on the grid size. If the grid size is denser, you can have a smaller value. I used like 5 one time if I had a really dense grid and it worked perfectly fine, but you need to converge your result with this smearing. With a coarser grid, you want to have this to be larger for even like 20, for example. And the pH frequency cutoff is that we're throwing away phonons below 1 MeV. This is just to prevent divergence at gamma point, but sometimes you don't need this cutoff either. The QDIMs are the phonon grids. So there's a K momentum and Q momentum, and this is the Q momentum for phonons. It has to be commensurate with K, just like the transport case. Here, I'm setting it to 20 for a faster calculation, but you can set it to anything like 60 or 30 or 10. And then we have the same energy and band window as setup, which is also very important. And finally, we want to compute our scattering matrix elements. So load equals to false by default, and we store them in this temp folder specified here. I also renamed my YAML file to gas dyna init because I don't want it to be overwritten. There's a default name that's called prefix calcmode.yaml. And I finished the calculation on my computer, but I was wondering if anyone finished theirs or still waiting. Okay, so if you look at the outputs, we'll see there's a cdyna file that we will need to use to generate the pump pulse with Perturbo-pi. There's a dyna init YAML file that contains all the inputs and information that we want. And this pulse out is just the output here. Okay, so in the cdyna file, you'll see 3 different data sets or groups. There is a band structure in Rydberg. We have only one band for the conduction band, so that's 1. And then this is the number of K points here that's involved in the energy range. The dynamics run 1 group is because we have only run dynamics 1 time. If you hit restart and do it again, then you have another group called dynamics run 2 that has the next run. The number of runs will be 1 because we only did it 1 time. After restart and doing it again, we'll have number 2 here. If you look at dynamics run, it has 2 snapshots. One is time equals 0, and because we set our bolts in step, the number of time step to be 1 for fake dynamics, so there's only 1 more extra time step. And these are actually all zeros because we technically didn't do anything. We had no electrons. We didn't put anything in there as our initial condition, but we will override this cdyna file as we run the real dynamics. And then you can also look at the YAML output file on your own to see what's in there, but we will need these 2 files for the pump pulse. So now we will do the same things for holes. I will copy paste this file. The only thing that's different is the energy range and the band range, and that hole equals to true, but everything else the same. Okay, so I will do the same thing here and wait for it to run. Any questions at this point? Okay. So while it's running, I just want to show that for the cdyna elec file, you have this temp folder, and in this temp folder stores all the electron phonon matrix elements. So if you look at temp, there is an HTF5 file that is called EPH, G2, which is G squared, and P1 is task or process 1. If you use multiple MPI task, then the number of files will be corresponding to the number of MPI tasks. This is because we break down all the scattering channels into different MPI processes so that you can run them in parallel. If you want to reuse these, you need to set load scatter EPH to be true. So if you're using the reference results, you want to set this load scatter EPH to be true and run the simulation. So read the temp file, but you need to have the same number of MPI tasks as the same number of files here. Otherwise, it wouldn't work for load EPH. Okay, so now we come back to see the holes. The holes are finished, and we have these two files. So now we're ready to generate the pump holes using Perturbo-py. Docker contains Perturbo-py intrinsically, but you can also download it and find the documentation here. We saw that we already have these YAML files and cDyna files under both directories. Then we can use this following script, which I have here, called generate pump_pulse.py. If you haven't finished the setup calculations and the pulse calculation, don't worry. You can use the cDyna TET file. There's also the grid file tet.h5 and then the init YAML in our reference folder and run it in the parent directory. It will also work. So I will briefly explain how to use Perturbo-py to generate this pump pulse. So the first thing is to set the folder names and find these following files. So I'm specifying the path to the electron, cDyna, TET, and dyna init YAML, which is the mock dynamics that we just ran. And then you want to see that we are importing these paths together to generate this dyna run object in Perturbo-py. And it's the same thing for holes. You can print them to see what it looks like. And then here is the whole command to generate the pump pulse. So there are many parameters that you can specify for pump pulse, and I'll explain all of them here. So the first thing is the pump energy in electron volts. It sets up how large the energy is. You can convert it from your wavelength. And then you want to specify the HDF5 file, which contains all the snapshots, the fpump snapshots in a certain path. You usually want to put them back in the cDyna folders, but you can put it anywhere as long as you differentiate the electrons and holes. So here I'm naming them to be ePump equals the pump energy for electrons and holes. And I'm putting it back into the cDyna elect and cDyna hole folder. There's the pump time step, which is the snapshot time steps in femtosecond. If you specify it to be 1, for example, in the dynamics run, you need to first run with time step of 1 femtosecond as well to match this. But after the pump duration, you can restart the calculation with a new time step of whatever that you want. And so you don't have to do the same time step anymore. But for the pump duration, you need to match the time step. Otherwise, it will be very confusing for Perturbo that it doesn't know what time step to use. And then the next one will be pump factor, which is just a factor in front of the whole pulse profile. So you use this factor to scale the whole pulse to match the carrier concentration, which we'll show how to do. And then the next one will be the spectral width for width half maximum in electron volt, and the duration for width half maximum in femtosecond. And then the pulse time window is 50 femtosecond, which is the entire duration of the pulse. So in this case, we will have to at least simulate the dynamics up to 50 seconds, and it's technically 51 steps that you need at least in your cDyna input later. The final width equals to true should be turned on for a Gaussian pulse in time and energy. If you just want a step function in time, then you can set it to be false. The transient dipoles, which would be taken here as transient dipole amplitude squared. This should be a NumPy file that contains the dipole amplitude square in the following dimensions. I don't have this here. I think I have it somewhere in this tutorial. But the dimension has to be number of electrons, number of electron bands, number of hole bands, and then number of key points. So electron, hole, and key points. If you specify anything in that NumPy file and specify this file, then you can read it here. If you specify it to be none, then it will just use 1.0 for the transient dipole amplitudes. So for simplicity's sake, we're doing 1.0 in this simulation. But for more accurate simulation, you need to compute this transient dipole from, for example, YAML and import it here. And there's a couple things for plotting, which is animate the pump pulse equals to true. You don't have to do it. If you want to visualize the pulse, you can also plot it with a scaling, which basically scales your carrier number F and K times this number so that you can see the dot on your file. Finally, the CNUM check equals to true will help you scale your carrier concentration. So if you want to calibrate that, you need to turn that on. Okay, so now we can run this. Using Python 3, and then I will have some folders. The first one is that we did have a pump pulse HDF5 file in ELAC and the same in holes. This is pump pulse hole. And then you can see what's listed in this pump pulse HDF5 file. So we basically have the same thing that we just input. I just wanted to highlight the energy profile is the pulse shape in energy. It has two lines. So one line is energy grid and one line is the pulse amplitude. And same for time step, you have 51 step because you have a time equals 0 to time equals to 50. And then the pump profile, a pump profile in this. And then everything else we already input except for the optional parameters, which is 10 numbers that you can specify to mark your HDF5 file. Because sometimes you have slightly different pump shapes and things you want to mark, but if you name this file name to be like 5,000 characters long, it's impossible. So you can store some optional parameters to mark this file, which can you can just use the same function and just add a line about that to store your optional parameters here. It's not really used in any Perturbo simulations. It's just for you to mark the file. But if you look at the pump pulse snaps, that's the F pump that we have. Because we have 51 steps, so we'll have 51 snaps. And we see that the number is number of key points and number of bands. So this will be used in Perturbo to be added to your df/dt equation every single time step. You can also specify and create your own pump pulse file as long as you have the following data sets and they are consistent with each other. So then you can use your own customized pump pulse instead of using Perturbo-Pi to generate it. The pro will be that you don't have to do both electrons and holes. You can do either one of them. Any questions up to this point? Okay. So to compute and calibrate carrier concentrations, what we did is that if you found this new folder in both CDNN and ELAC and holes, is the CNUM check folder. If you go into it, you'll find a CDyna file, and it contains the accumulated electron populations generated over the entire pulse that you specified. So it's added up. And then with this, you can compute the carrier concentrations. So this contains the F and K as a function of time. So the first thing we want to do is to integrate it over the momentum space to find the population as a function of energy, and then we'll integrate over the energies. So in order to do that, we can use dynamics PP, which we use for post-processing and integration over the entire momentum space. So what we can do is we first need to link the APR file that's 2 folders above, link the TET file that's 1 folder above, as well as the temper. You can also copy these files as well. and you use the following input for post-processing. What's different is the calc mode is dynamics PP, and then you have this both DE, that is the energy grid that you want to integrate over in milliantron volts. So if you use pp.in and run Perturbo, you will have a gas popule.h5 file that contains the F as a function of E and T that you want. You can use the pp.in to treat your dynamic simulations as well to visualize the plots I showed in the lectures. And you also have a YAML file, but what we really want to see is the DAT file, which contains the carrier concentration. So if you look at DAT file, it just basically gives you the accumulated carrier number over per unit cell. And the unit cell volume is stored in the EPR file in terms of atomic units. So with these information, you can then compute the carrier number or concentration per centimeter squared, and then you can calibrate this carrier concentration. So after, for example, you compute this, and this is like 10 to the negative, sorry, 10 to the positive 18 per centimeter squared, and you're like, oh, this is not good enough. I want to have twice the number. Then you just go back to the generate pump pulse, and then change your pump factor to 2 times that, and regenerate the pump by running this Python script, and then you will be good. Any questions? Okay, if no questions, for the last 10 minutes, we would like to finally simulate the dynamics using this pump pulse that we generated. So we will first simulate the electron dynamics. The dynamics run is the same, so I can copy my pulse in, which is in calc mode dynamics run, and just modify the time stepping. So in this dyna in input, I want to change the number of in steps because we want to simulate a longer time. And after running this whole script, we will override the cdyna file that was fake before for generating the pump pulse. And then the next step, I want to, for example, output every 20 step. If you want fewer outputs, you can say output every 50 step or 100 step. It's up to you. I will say 20, and then the time step will be 1. So now we'll have 50 steps in our final cdyna file. And then we want to reuse the EPH scattering matrix elements that we computed that took like 5 minutes for my computer. So I want to specify it to be true in this case. And I will also use one MPI task so that I don't mess up the files. The same temp folder has to be specified. And then finally, we have to set pump pulse equals to true. And then the file name needs to be basically where the pump pulse is stored. So in this case, I store it in this folder, calling it this name. So I'll just put it here as my pump pulse name. And finally, we note that if you want to reuse these scatter, low scatter, you cannot change delta smear with frequency cutoff and phonon Q grids because they're all dependent. The EPH scatter matrix element values are dependent on these values. But for the YAML name, I will just set it to the default name, which is an mxrun, so I don't overwrite the previous YAML file that I generated, just to keep the record. Okay. And as I said, you can use 1 femtosecond to run however many long time steps, but if you just want to use a different time step, you can first run 51 step here to cover the pump pulse duration, and then restart with both init equals to restart, and restart with whatever time step you want. That will converge the results. So now I'm using 1000 to run into 1 picosecond. After specifying these, I'm ready to run. This calculation should take relatively less time. If you're just interested in the electron populations, you can stop right here after it and process your output in CDyna, which contains the time-dependent electron populations. But if you also want to look at the holes, you can do the same things for holes. So here I'll also copy paste Dyna in and then modify it. The same things need to be modified. Here I want to be 20. I want to load my files. It's true. And then I want to read the pump post file here. Finally, I just want to change the YAML file name. Okay. So now we're ready to do the same things for holes. And then you can see that the pump pulse, if you use pump pulse equals true, it will produce some of these outputs so that you can verify what you have done. And we just finished the dynamics. Notice that the grid size is 60 and 20 for phonons, electrons and phonons. This is not going to be converged by any chance with polar materials like gallium arsenide. So I strongly recommend you using a much denser grid size to see the changes. And finally, we can see that we have all these CDyna H5 files that's overwritten. So if you want to look at what happens in the dynamics run here, as I said, we have 50 more steps. So it'll be snap 0 to snap 50. And it contains all the F and KT that we want. If you want to integrate them, you can integrate them to F as a function of energy using dynamics PP, which we will not show here, but you can find it at the bottom of the tutorial or for additional resources. But I just want to briefly showcase the utilities in Perturbo-Pi, where we can compute the transient absorption. So what we do is we go back to the parent directory, and we have this script that uses Perturbo-Pi. So in this script, you construct the DynaRun object again, but in this case, we have a new CDyna with actual dynamics, and then a dynamics run YAML. That's the latest YAML file. After constructing the DynaRun for electrons and holes, you can compute the transient absorption signals for both using the spectrotrans absorption, compute trans absorption. There are some parameters that are listed here. You can just use these parameters, but the E grid is the energy grid size in electron volts that you're integrating over, and the energy grid max is the maximum energy in this transient absorption signal that you want to integrate to. But if you set it to none, it will just be the band gap. Well, not the band gap, the maximum energy difference in your whole range. So for example, for us, it will be 6.7 electron volt to 4.9. And then finally, this eta is the Gaussian energy approximation that we specify for integrating these signals. And if you want to save the transient absorption, you have to specify save numpy equals to true. It also is dependent on the transient dipole squared, but I'll put it to none, which is 1.0 here. You can also input your numpy file to make this non-zero, not a constant. So now we'll run. Now we run the compute transient absorption. I will skip these information that you can read on your own, but what it does is that it saves all these numpy arrays. The first one is the energy profile or the energy grid for your transient absorption signal, which is 0 to the maximum energy difference. This is time grid this is from 0 to 1 picosecond. And then the 3 DAs are the transient absorption signal for total electron plus holes, electrons, and holes. And these are in the dimension of energy grid points and number of time grid points. So the length of this and the length of that. And then finally, I just want to plot this. You can just plot this with all these NumPy files on your own. But if you just want a simple script, there's a simple script here that's called plot transabsorption. And you can use this to plot. So to summarize what we did today, we generate a pump pulse. And remember that we chose animate, so we can actually look at the pump pulse shape that we did in a GIF file called pump pulse GIF. We have these bands and conduction bands and valence bands. And because we have a very coarse grid size, and that's the only points on this path that we generated with the electron populations as a function of time during the pulse time. And then with this pulse added, what we find is these transient absorption signals. And if we look at the plot, which is stored in this PNG file, you'll see this transient absorption in gallium arsenide. The reason it's not cooling or decaying is because the grid size is extremely coarse. So I attached a file that uses a much denser grid size, like 180. This will take several hours to run on one node on a supercomputing cluster. But you will see that there is indeed a decay and carrier cooling here. I think that's the end of the tutorial. And are there any questions?